double angle, power reducing, and half angle formulas. So all the formulas we're going to be learning in this section are consequences of the addition formulas we learned in the previous section. The first group of formulas, which is the double angle formulas, are going to allow us to find the values of the trig functions at twice the angle from their values at 1 times the angle. Okay, and the other one of the other two groups, the half angle formulas, are going to relate the values of the trig functions at half the angle to their values at 1 times the angle. Let's take a look at the first set of formulas. So the double angle formulas, we have one for sine. So sine of twice x is 2 times sine x cosine x. Formulas for cosine, we have 3, they are all the same. For cosine of 2x, and they are displayed on the screen. And the last one, it's a double angle formula for tangent, which relates as well. The tangent acting on twice the angle to the tangent acting on just 1 times the angle, right? I mean, just quick observation, all the entities on the left hand side are trig functions acting on twice the angle, and all the functions on the right hand side, they are trig functions acting on 1 times the angle. Okay, so this is what the double angle formulas, this is what these formulas are about. All right, so let's prove them. I'm not gonna show all of them. I'm gonna just say that they follow immediately from the addition formulas that we showed in the previous section. As said earlier, I'm gonna just show the cosine ones. So I'm gonna show all these 3. So let's prove. Let's prove that. So proof. Cosine of 2x. How about we look at this as cosine of x plus x, right? Cosine acting at twice x is the same as cosine acting at x plus x. And from the previous section, we know that cosine of a sum is equal to cosine of one of them. So x times cosine of the other, which is also x, right? Minus cosine of the second, sine of the second. So sine of the second, or the first, times sine of the second. Okay, both in this case, both of the angles, they are both x. Okay, so we get this. All right, and this is cosine squared x. Why it's cosine squared? Because it's cosine x times cosine x, and cosine times cosine is the square of cosine, minus sine squared of x. So similarly here, sine times sine of the same angle, it's the square of the sine of that angle. So we get this. So what did we show? We showed that cosine of 2x is equal to this, right? So we showed the first one. So this is okay at this point. How about the second? Why this guy is equal to the second? Well, let me choose a different color. So this is also equal to, by the Pythagorean identity, I know that cosine squared of x is equal to 1 minus sine squared of x. Agree with that? So we have this. And this means instead of cosine squared, I can look at it as 1 minus sine squared. So this becomes 1 minus the square of sine x. This is replacing cosine squared because of this identity again, minus sine squared of x, right? Minus sine squared of x. Okay, and what is this? Isn't that 1 minus 2 times sine squared of x? Isn't that 1 minus 2 times sine squared of x? And why is that? Because look, this is the same guy minus itself. So something, maybe I should say that these parentheses are just for decoration. They're not doing anything, okay? So 1 minus sine squared x minus sine squared x is 1 minus 2 sine squared x, okay? Minus something minus itself is minus 2 times the thing. All right, so this takes care of This takes care of this one, right? It takes care of this. And the last one, so I need 2 cosine squared instead of 2 sine squared. So I'm gonna go back to this, and how about now, instead of replacing cosine squared by 1 minus sine squared, how about replacing the sine squared as 1 minus cosine squared? Okay, how about doing that? Let me separate the two by a bar here. And so once again, this is also equal to, because of this formula again, okay, but now backwards. Okay, let me write it again. So backwards this time. This is because sine squared x is equal to 1 minus cosine squared x, right? So what I'm gonna get that this is equal to cosine squared x minus, so instead of sine squared, I'm gonna replace it by 1 minus cosine squared. And where does this come from, this formula? This is the Pythagorean identity. This is the same thing as this. Okay, they're the same. So we get that this is equal to 1. So sine squared is 1 minus cosine squared of x. Okay. All right, and what is that? This is cosine squared of x minus 1 plus cosine squared of x. So minus, I mean, if you want to destroy the parentheses, everybody inside has to switch sign. So minus 1, and minus the minus becomes a plus cosine squared. Okay, and cosine squared plus itself is twice cosine squared minus 1. Okay, and this is exactly what we wanted. It's right there. Okay, so this has also been proved. Okay, all right, so as we said, sine is you can also see it as sine of x plus x, and use the addition formula for sine, and tangent as well. Okay, so I encourage you to actually try to prove them. All right, let's put them in action. Let's go to the book. This is section 0.3. This is on page 597, and let me do a few problems. Let me go to the next page. Let me do one of these problems from 7 to 14. How about doing 10? How about doing 10? So what's the question? Use the given information to find the exact function values. And here I have 3 parts. I have sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. And they told us that cosine of theta is -5/8, and theta is in quadrant 3. Okay, so from this information, I have to find sine 2 theta, cosine 2 theta, and tangent 2 theta. All right. So this is on page 598 and number 10. Okay. All right. So I have that cosine of theta is equal to -5/8, and that theta is in quadrant 3. So the question is to find sine of 2 theta, cosine 2 theta, and tangent 2 theta. Let's start with the first one. Sine of 2 theta. Sine of 2 theta. What does the double angle formula tell us? Well, sine of 2 theta is 2 times sine of theta cosine of theta, right? So I'm replacing x by theta, and this reads sine 2 theta equals 2 sine theta cosine theta. So this is then 2 sine theta cosine of theta, right? Do we know cosine of theta? All right, great. So we know this. We know this guy. We're still missing this piece, right? We're still missing this piece. Let's try to find it. sine of theta, how can I relate sine of theta to cosine of theta? This is a typical situation, right? I would love to have sine of theta, information on sine of theta, but I do have information on cosine of theta and where theta lives, in which quadrant. Well, Pythagorean identity, right? It's this one. It's this one right here. So I know that sine squared of theta is equal to 1 minus cosine squared of theta. It's right there. Okay. And what's cosine of theta? It's negative 5 over 8. So I get 1 minus negative 5 over 8 squared. Agree? And this is the same as 1 minus 25 over 64. Right? Okay, I'm doing the same denominator. That's gonna yield denominator 64, and here I have 64 minus 25, which is equal to 39 over 64. Okay, so what can we then infer about sine of theta? Well, sine of theta is plus or minus the square root of 39 over 64. We still have to determine the sign, whether it's plus or minus. Well, what do we know about theta? Theta lives in the third quadrant. Theta lives in the third quadrant. And in the third quadrant, if we have a small picture, in the third quadrant, okay, in the third quadrant, what can we say about an angle in the third quadrant? So something like this. Well, the angle in the third quadrant is gonna have a terminal point whose first coordinate is negative, right? The first coordinate is negative, and the second coordinate is negative, right? So the second coordinate is the sine. The first is the cosine, which is negative. They gave it to us, and the second is the sine, which should also be negative, right? Because the y value here is negative. So it's that guy then. It's that sine. So I'm gonna erase the other piece. So I'm gonna erase the positive sign, right? Okay, very good. So I know now what sine of theta is. So I can go back and replace it and get myself the sine of twice theta. So let's do that. So sine of 2 theta is then equal to 2 times the sine theta, which we just found to be negative square root of 39 divided by 64. And by the way, let's simplify this before we actually copy it. Square root of 39 divided by 64 is square root of 39 divided by 8, right? So it's square root of 39 divided by 8. I cannot simplify square root of 39 anymore because 39 is made up of 3 and 13. Okay, the prime factorization of 39 is 3 and 13. None of them is a perfect square. So that's a simplified version of this expression. And now if you copy it, we're gonna get here, let me reduce this umbrella here, so we're gonna get this divided by 8, right? So that's the sine of theta times cosine of theta, and cosine of theta was given to us. This is the negative 5 over 8. So times negative 5 divided by 8, right? Okay, and how much is this? How much is this? So we can simplify by 2. If we simplify by 2 here, we get 1, and here we get 4. Am I correct? So downstairs we only get 8 times 4, which is 32. Which is 32 downstairs. And then upstairs we get negative times the negative, which is plus. So we get 5 square root of 39. Okay, so this is sine of 2 theta. All right. And the other question is they want us to find cosine of 2 theta. So cosine of 2 theta. So this is part B. Cosine of 2 theta. Okay, let's go back to the double angle formula for cosine. We want to find cosine of 2 theta. We have 3 to choose from. They're all the same. They're all the same, and we actually show them. Let's choose any of them. I mean, look, any of them, we have all the ingredients for any of them, right? Because we have cosine of theta and we have sine of theta at this moment. And for this one, it requires only sine, and for this one, it requires only cosine. Okay, so you choose. How about you do all 3 at home? Okay, I'm gonna choose one of them. Let's choose the last one, 2 cosine squared theta minus 1. So 2 cosine squared theta minus 1. Okay, all right, and this means 2 times the square of cosine theta, and we know what cosine theta, they gave it to us. It's negative 5 over 8 minus the 1, right? Okay, and that's 2 times 25 over, right, because the negative 1 squared is plus 1, 5 squared is 25, and 8 squared is 64 minus 1, right? And if you want to simplify by 2 here, if you want to simplify by 2, you get 1, and here you get 32, right? Okay, and this is then 25 over 32 minus 1. All right, then how much is this? What's 25 minus 32? Divide by 32 minus 1. This is 25 minus 32 over 32, if you make the same denominator, correct? And this is minus 7 divided by 32. Sounds good? Okay, and obviously this is simplified. This is in lowest terms because 7 doesn't divide 32. Okay, so this is part B. And lastly, part C, we need tangent of 2 theta. So let's go revisit the function, the equation that relates tangent 2 theta to a trig function acting on 1 times the theta, and this is the recipe: 2 times tangent theta divided by 1 minus tangent squared theta. Okay, so let's write this down. So this is equal to 2 times tangent of theta divided by 1 minus tangent squared of theta. So the only ingredient needed in this quotient is tangent of theta, right? It's needed upstairs and downstairs. So let's find that. Let's find tangent of theta. Well, what's tangent of theta? This is sine of theta over cosine of theta, and we know each one of them. We know what sine of theta is. We found it here. It's right there. Sine of theta is minus square root of 39 divided by 8. So minus square root of 39 divided by 8. And cosine of theta, they gave it to us. Cosine of theta was minus 5 over 8. Correct? Okay, so this is the same as the negative divided by the negative is positive. We get square root of 39 over 8. Dividing by 5 over 8 is the same as multiplying by 8 over 5. And then if you simplify by 8 here and here, we only get square root of 39 divided by 5. So this is tangent of theta. Okay, so that's the piece that we were missing in this recipe. Let's take this package and employ it right there at this point. Okay, so we get 2 times the tangent of theta that we just found, which is square root of 39 divided by 5. And downstairs I have 1 minus the square of tangent of theta, which we just said is square root of 39 divided by 5. Agree with that? So we get this. Alright, and if you want to simplify it, again, for the purpose of our course, you don't need to simplify. This is as good as anything else. But if you insist to do so, we get what? We get 2 times square root of 39 divided by 5 And downstairs I have 1 minus, what's the square of the square root of 39? It's 39 divided by the square of 5, which is simply 25, sorry. Okay, 25. Okay, and this is how much? 2 square root of 39 over 5, and the whole thing is divided by, how about we do the same denominator, which is 25, right? And 25 minus 39 is negative 14 over 25, right? Okay. And this is then equal to 2 square root of 39 over 5 times the negative 14 divided by the negative 14 over 25. And dividing by negative 14 over 25 is the same as multiplying by 25 divided by negative 14, right? And that negative can be just at the level of the fraction bar. We get this. Make sense? Alright, let's simplify as much as we can. If you divide 14 by 2, you get 1 here and you get 7 here. And if you divide the 25 with the 5, you get 1 here and 5 here. So putting things together, we get minus 5 square root of 39 divided by 7. Okay. So this is what tangent 2 theta is equal to. Let's go back to the book. Still on the same page, 598. And let's do one of these problems from 15 to 20. The question here is find the exact value of the expression. And let's do the last one, number 20. 2 cosine squared of minus 165 degree minus 1. Okay. So let's do number 20. We want to find the exact value of this expression. Well, the first observation is that what I'm going to do is I'm going to try to get rid of this minus. Cosine is an even, I get it for free, right? Because cosine is an even function. Cosine acting on negative theta is cosine of theta. So that's the same as, let me just go back to purple. So that's the same as 2 cosine squared of 165 degree minus 1. Okay. All right, and 165 degree is not a remarkable angle. Why? Because what's the reference angle for this angle? 165. 165 is slightly less than 180. And what's the reference angle here? What's that angle? It's 15 degree, right? It's 15 degree, and certainly 15 degree is not remarkable. So except, if you use a calculator, you get an approximation of it. You don't get the exact value. So we're going to appeal to one of the formulas we just learned, one of the double angle formulas we just learned, and this looks to me, this is the same as 2 cosine squared theta minus 1. If you think about 165 degree as theta, so this becomes 2 cosine squared theta minus 1. If you go back to that formula and try to relate it to twice the angle, you get cosine of 2 of that theta, right? So because what we have is of this format, 2 cosine squared of 165 minus 1, it's cosine of twice the 165, correct? So that's equal to cosine of twice 165 degree. And let me be very, very clear here, because what am I using? I'm using that 2 cosine squared of theta, okay, minus 1 is equal to cosine of twice theta. That's what I used. Okay, and then this is the same as cosine of, what's 165 degrees times 2? This is 330 degree. Okay, 330 degree. And as such, what's the remarkable angle? It should be twice, sorry, what's the reference angle? It should be twice the old reference angle, which is 15. So twice 15 is gonna be 30 degree. Let's make sure. So what's 330 degree? What is it on the picture? 330 is gonna be somewhere in the fourth quadrant, right? So this is 330 degree. Okay, and what's that angle here? What's this? A reference angle. The acute angle that separates this angle from the x-axis. It's gonna be 30 degree, right? As expected, twice the old reference angle, which is 30 degree, because we got twice the previous one, right? 165. We got here 330, which is twice the 165. So we get the reference angle to be 30, which is certainly a remarkable angle, right? Which is certainly a remarkable angle. All right, so what do we get? We get that this is equal to cosine. Remember, it's going to be plus or minus the same trig function acting at the reference angle, which is 30 degree. And which one is it, the plus or the minus? Well, this is dictated by where theta is, where this 330 degree is. It's in the fourth quadrant. And what's the sign of cosine in the fourth quadrant? What's the sign of cosine of the fourth quadrant? Cosine is positive here, right? So the sign is going to be plus. So the sign is going to be plus. So I'm going to erase this. I'm going to write plus, right? Remember, trig function acting at an angle is equal to plus or minus, which has to be determined, of the same function, the same trig function acting at the reference angle. And the reference angle here is 30 degree. Okay? And what's cosine of 30 degree? This is square root of 3 over 2. Makes sense? So that whole expression is simply square root of 3 over 2. Okay. All right, let's continue. Back to the book. How about we move on to this set of problems, 21 to 34, and let's choose one of these. Which one should we choose? How about 34? About 34. We want to show that cosine of 4 theta is equal to sine to power 4 theta minus 6 sine squared theta cosine squared theta plus cosine to power 4 theta. Okay? So let me write this down. So this is number 34. We want to show that. We want to show the identity. So we want to show cosine of 4 theta is equal to sine to power 4 theta minus 6 sine squared theta cosine squared theta, plus cosine to power 4 theta, right? Okay. All right, I'm gonna start from the left-hand side. So I'm gonna start from the left-hand side, which is cosine of 4 theta, and I'm gonna see it as cosine of twice theta, correct? 2 times 2 times theta is still 4 theta, so I'm still talking about the same entity. And now all of this guy, think about it as one thing. So this becomes cosine of twice the asterisk. Cosine of twice the asterisk, if you go back to the double angle formula for cosine, you have 3 choices to choose from. Okay, which one should we choose? Well, first let me tell you what x is. Here I have cosine of 2 times the 2 theta, so that x is our 2 theta in our context, which is referred to as the asterisk, correct? So I have 3 to choose from. Let me keep an eye on the desired conclusion. So I would like the conclusion to involve sine and cosine, right? I would like the conclusion to involve sine and cosine. So how about using the very first one? How about using about using cosine squared of the asterisk, right? The asterisk minus sine squared of the asterisk, right? This is what the formula says. It says again, cosine of 2 times something is equal to cosine squared of the thing minus sine squared of that thing, right? And who's our thing here? It's right there. It's 2 theta. So who's gonna take the role of this asterisk here and here? The 2 theta, right? So this is 2 theta here and here. Make sense? All right. And cosine squared of 2 theta. So this is the square of cosine 2 theta, right? So this is the same as the square of cosine of 2 theta minus the square of sine of 2 theta. Sine of 2 theta. Okay. So I'm gonna reuse these double angle formulas that we just talked about. Again, one time for cosine and one time for sine. Okay, and what do we get? This is the square of cosine of 2 theta. How about rewriting it using the very first formula and the formulas for cosine? So cosine, I'm using the same one I used here, right? Cosine squared of the angle, which is theta in this case, minus sine squared of that angle theta, right? Again, I'm using the same property I used here. So how about I label it for you? So over here, what did I use? I used that cosine of twice the asterisk is equal to cosine squared of the asterisk minus sine squared of the asterisk, right? So this is the property used before. And this is the same property I'm going to be needing here. I'm going to need the same one. Because this is still of the format cosine twice something. Cosine twice something is cosine squared of the thing minus sine squared of the thing, right? So I got it here. Now for this guy I have minus the square of sine of 2 theta. And if you go back to the double angle formula for sine, this is 2 times sine of theta cosine of theta, right? Okay. All right. And how do we simplify this? How do we expand? So do you recall the formula about squaring a difference? So how do you square a minus b? If you FOIL this out, if you forget the result, you can FOIL it out. The result is a squared minus twice the product ab plus b squared. Okay. So let's apply it for this guy here. Who's gonna take the role of a? It's the cosine squared. And who's taking the role of b? It's the sine squared. So here it becomes cosine to power 4, right? All right, let's do it in steps. This is cosine squared of theta to power 2, correct? Because a is cosine squared and b is sine squared. So it becomes the square of a, so it's the square of cosine squared, minus 2 times a times b, so minus 2 times a, and how much is a? Cosine squared of theta, and times b, and how much is b? Is sine squared of theta, correct? Plus the square of b, so plus the square of b, which is sine squared theta. This is what b is, right? Okay. And then minus the square of this guy. Don't forget, this guy is made up of 2 times sine theta times cosine theta. If you multiply this by itself, this is what the square means, right? 2 times the 2 becomes 4. Sine theta times sine theta becomes sine squared theta. And cosine theta times itself becomes cosine to power 2 theta, right? All right, and what is that? What is that? What's cosine? What's the square of the square? What's the square of the square? It's that thing, the base to power 4, right? 2 times 2 is 4. So you get cosine to power 4 theta minus, look at this, minus 2 of this guy. And here I have minus 4 of the same guy, right? This is the same guy. So what's minus 2 minus 4? Isn't it minus 6? So minus 6 of that guy, which is cosine theta times sine squared theta. Because it's the same. Think about it as an image, right? Forget about the details. Think about this as an image. Minus 2 times an image, minus 4 times the same image. Well, this is minus 6 times the image. Okay, plus, how about this? The square of the square, we just talked about it. This is the sine, the base, to power 4, because you multiply the powers, right? 2 times 2 is 4. We get this. And let's contrast this with what we wanted. Isn't that what we want? Isn't that the same as what we wanted? Yeah, it's the same. Correct? All right. Moving on. Let's now mention and prove the power reducing formulas, and these formulas are going to allow us to write any trig expression involving even powers of sine and cosine in terms of the first power of cosine only. And this technique is important in future courses, especially in the calculus sequence. So it allows us to write, look, even powers of sine and cosine. So here I have second degree sine, and here I have second degree cosine, and you can transition from second degree sine or cosine to what's the active ingredient on the right side in both of them? Just cosine, and with power 1, cosine power 1, right? So this is what this is saying. And if you go to power 4, if you have power 4, you break it down, you go to power 2 and then to power 1, right? Makes sense? So what I'm saying here is that if you have, for instance, sine to power 4x, let's say, okay? Because here it says even, it doesn't only say 2. So what can we do? What we can do is we can do sine squared of x squared, right? And rewrite this guy in terms of cosine, correct? In terms of cosine. So here I'm gonna get something in terms of the square of cosine, and then use this to transition back to degree 1. Okay, so this is how things are gonna unfold from even power, any even power, all the way. You keep breaking it down all the way to the first power of cosine. This is what these two lines are saying. I'm trying to explain what this paragraph above is trying to illustrate. All right, so where do these formulas come from? Well, if you just think about it for a second, look at the first one. This is the same as 2 sine squared, right? This is the same as 2 sine squared of x equals 1 minus cosine of 2x. I'm talking about the first formula. This is the same as if you multiply both sides by 2, you get this, right? And that's the same as cosine of 2x is equal to 1 minus 2 sine squared of x. Make sense? So, I mean, just add by cosine of 2x and subtract by 2 sine squared x, right? Move them around, you get this. And this is a formula we just proved above. This is one of the double angle formula for cosine, correct? So what is this then? This is simply going back to the double angle formula for cosine and just solving for sine squared, right? You just solve for sine squared here, you get this formula. Make sense? And how about this? Cosine squared x equals this. Where does this come from? How about we unravel, or we cannot trace it back? This is coming from, well, this is the same thing as saying 2 cosine squared x equals 1 plus cosine of 2x. Correct? If you multiply both sides here by 2, you get this. And isn't that the same as cosine of 2x equals, if you subtract both sides by 1, don't you get 2 cosine squared x minus 1? And do you recognize this? This is one of the other formulas for one of the other double angle formulas for cosine. correct? So where does this come from then? This is just going back to this double angle formula for cosine and solving for cosine squared. Solving for cosine squared, you get it? Makes sense? And the last one, how about the last one? Where does it come from? Tangent squared x equals 1 minus cosine 2x divided by 1 plus cosine 2x. Well, tangent of x is sine over cosine, right? So tangent squared is going to be sine squared over cosine squared. So it's going to be this sine squared divided by cosine squared of the same angle, x. So you get this guy over this guy. And what's this quotient between this and this? Isn't what you see on the screen. Isn't this guy then? Okay. So all these formulas they just follow readily from the double angle formulas, and the last one is just this quotient divided by this quotient. Makes sense? Alright, so I'm not going to write the proof because the proof is trivial. So I'm going to erase this part. Even though we kind of did it, right? Okay, let's go back to the book, and let's do one of these problems from 35 to 38. These are power reducing formulas. Power reducing because they reduce powers, right? The power decrease from 2 all the way to 1. 2 all the way to 1. 2 all the way to 1 here, right? The power on the right hand side, all the powers are on the right hand side are 1. Okay. Alright, so let's choose one of these. How about 38? Okay, how about 38? So I wanna write 38. And what's 38? This is cosine to power 4x plus sine squared of x. And what's the question? The question is, write the expression in terms of first powers of cosine. Just first powers. Alright? So cosine to power 4x, well, as we said, this is the same as cosine squared of x squared plus sine squared of x, right? Okay, and this is the same as the square of cosine squared x. And what's cosine squared x? It's 1 plus cosine twice x divided by 2 plus, which plus I'm talking about? It's this plus the square of sine x. And in terms of cosine, first power of cosine is going to be 1 minus cosine 2x divided by 2. So 1 minus cosine 2x divided by 2. Okay. So once again, I wrote cosine to power 4 as the square of cosine squared, and cosine squared, I have a relationship between cosine squared and the first power of cosine. It's right there. And then I rewrote the sine squared of x in terms of first power of cosine. So I get this. Alright. And this is what? This is, well, the square of this is going to be, well, downstairs is power 4 for sure. Sorry, it's denominator 4 because it's the square of 2. And upstairs, this is the square of the sum, which is 1 plus cosine 2x plus that quotient, right? Okay. What's the square of his sum? What's the square of his sum? Let me recall it for you. What's the square of a plus b? This is the square of a plus twice the product between a and b plus the square of b. Correct? So let's use that. Let's use that where? Upstairs. This is the square of his sum. So who's going to play the role of a? 1 is going to play the role of our a here. And cosine 2x is going to play the role of b. Okay? Now what do we get? We get, so still 4 downstairs. And upstairs I have 1 squared, a squared, so 1 squared, which is 1, plus 2 times a, 2 times a, and a is 1, so 2 times 1, so 2 times b, which is cosine 2x, plus what? Plus the square of b, the square of b. So it's going to be the square of cosine of 2x, right? It's the square of my b, and this is my b, cosine of 2x, plus this other quotient that's sitting here, right? So 1 minus cosine of 2x. Sounds good? Okay, so the last thing I need, remember the question is to write the expression in terms of first powers of cosine, and this is certainly not the first power of cosine, this is a second power of cosine, right? I still need to rewrite this in terms of first power of cosine, and can I do so? Yeah, I just have to apply this lower or this power reducing formula, right? This one, but not this time, not with x, this time is with twice x. So every time I see x, I'm going to replace with 2x, correct? So I'm saying this guy can be anything, whatever that thing is. In my context, I have cosine squared of 2x. So I'm going to write instead of x 2x, and then I'm going to pick up a first power of cosine here. Make sense? Okay. So back down here. So this is 1. So let's keep this denominator 4. 1 plus 2 cosine of 2x plus, we just talked about cosine squared of 2x. That's going to be by the power reducing formula just talked about above. This is 1 plus cosine of twice my asterisk, which is 2x. Agree with that? So the formula says cosine squared of something, and this thing happens to be this guy. Cosine squared of something is 1 plus cosine of twice that thing divided by 2. I'm just applying the formula. Okay. Plus that other quotient, 1 minus cosine of 2x. Okay. All right. What is that? What is that? 2 times 2 times x. Isn't that 4x? Isn't that 4x? So what do we add? What do we have at this point? Everything here in the first quotient is over 4. So I have 1 plus 2 cosine 2x plus 1 plus cosine 4x over 2 plus that guy. Okay. All right. Okay, now we're gonna do some aesthetics. We're done. I mean, to answer the question, what's the question again? Remember, let's write the expression in terms of first powers of cosine, and take a look. Everything here is in terms of cosine, and all the cosines have power 1, right? This is cosine power 1 of twice x. This is cosine power 1 of 4x, and this is cosine power 1 of 2x. So technically we answered the question. But let's make it look, let's make this expression look better. Let's play a little bit of algebra here. What do we have? How about having the same denominator upstairs, which is 2? How about having the same denominator upstairs? So I want to have all this guy is to be over 2. As such, I'm going to multiply everybody upstairs with 2, right? So we get, let me move it to the next page. So we get what? We get 2 times 1, which is 2, okay, which is 2, plus 2 times 2, which is 4, cosine of 2x, plus 1 plus cosine 4x, right? And this whole thing upstairs is divided by 2, and the whole thing, this whole thing now is divided by 4, that 4, plus this quotient. 1 minus cosine of 2x over 2. Okay. Again, we're just doing aesthetic work at this point, just to make it look better. In other words, we're simplifying. Okay. And now look at this. If you have a divided by b and the whole thing is divided by c, So if you take a over b as the numerator and you're dividing it by this denominator c, isn't that the same as a divided by b divided by c? Same thing. And doesn't this mean that I have a divided by b times the reciprocal of c, which means 1 over c? One more time, dividing by c is the same thing as saying multiplying by the reciprocal of c, which is 1 over c. And all of this means, how do you multiply two quotients here? A times 1, which is a, divided by the product of the denominators, which is b times c. B times c, right? Okay, so that's what I'm gonna use to simplify all this writing. And let me be clear, the a is gonna be this guy. That's the guy who's playing the role of a in my discussion here. And that's the guy who's playing the role of b. And this guy is the c guy. Okay? Do you believe that this quotient here, the structure of this quotient is the same as the structure of this quotient? Okay, as such, what's the result? It's a divided by the product of bc. So it's going to be a, all this guy, divided by the product of b and c. So what's the product between b and c? It's 2 times 4, so it's going to be 8. Correct? So it's going to be 8. Okay, so let me write that. So I'm going to have all this block A, so 2 plus 4 cosine of 2x plus 1 plus 4, plus 4, cosine of 4x, divided by b times c, and b times c is 2 times 4, plus 1 minus cosine of 2x over 2. Okay? All right. And now we know that 2 times 4 is simply 8. And upstairs, can I simplify? 2 plus 1 is 3, right? 2 plus 1 is 3. Let me write that down. So upstairs is 2 plus 1, so 3, plus 4 cosine of 2x, plus 1 times cosine of 4x. I cannot combine, right? This is cosine of 2x. This is something, and this is a completely different thing. This is cosine of 4x divided by 8 plus 1 minus cosine 2x over 2. Okay? How about now having the same denominator between the two so we can glue them together? Again, we're still doing aesthetic work. How about multiplying downstairs by 4 to get an 8, which is to get a common denominator, and hence I'm going to also multiply upstairs by 4 to preserve that value, the value of the quotient. All right, and then what do we get? So since now we're going to have the same denominator, how about gluing them together? We get 3 plus 4 cosine of 2x plus cosine of 4x plus what? 4 times 1 is 4, and minus 4 times the cosine of 2x. Yes. Okay, and now do we have anything that can be simplified? Yes, we have the 3 and the 4, and the 3 plus 4 is 7. So the 3 plus 4 is 7. How about the cosine 2x? How about cosine 2x? Do you see they cancel each other, right? Plus 4 cosine 2x minus 4 cosine 2x, they're gone. And then I have plus cosine of 4x. Agreed? So we get this. Make sense? All right, so let's go back to the book. And let's do now number 45. So the question is, fill in the table for alpha in the given quadrant. What do you notice about the signs of sine of alpha and tangent of alpha over 2? So we're going to complete this. Table here. So the first row is quadrant for alpha. So if alpha lives in quadrant 1, what happens? If alpha lives in quadrant 2, what happens? And so on. Okay? So let me copy this this table and put it here. So this is number 45. All right, so if alpha is in quadrant 1, what does it mean for alpha to be in quadrant 1? Well, it means that alpha is between, let me write it here. So this means alpha is between, I'm talking about this case, when alpha is in quadrant 1, right? So this means that alpha is between 0 and pi over 2. This is what it means in quadrant 1, correct? Okay. And if alpha is between 0 and pi over 2, what can be said about alpha over 2? What can be said about alpha over 2? Well, divide through by 2, you get, if you divide through by 2, 2 is a positive entity, and if you divide by positive entity, you do not have to flip the inequality signs, right? So you get 0 divided by 2, which is 0, and alpha over 2, and pi over 2 divided by 2 is going to be pi over 4, right? Agree with that? So if alpha is in quadrant 1, again, I'm talking, quadrant 1 means it can be between 0 and pi over 2, or it can be between 2 pi and 2 pi plus pi over 2, right? But, I mean, the same treatment is going to be for, if you add here by 2 pi, right? Or if you add by an integer multiple of 2 pi, I mean, the same treatment. I'm going to just treat it for the very first quadrant where everything is in the first revolution, okay? All right, and try to convince yourself why it is the case if you add to, I mean, if you treated the first quadrant but in other revolutions, like more than one revolution. In other words, if you add here an integer multiple of 2 pi to both sides, why the same treatment becomes the same, remains the same. Okay, so again, if alpha is between 0 and pi over 2, alpha over 2 is going to be between 0 and pi over 4. We just talked about it. And how did we get to this point? By dividing through by 2. And dividing by 2 is since it's a positive entity, you do not have to reverse the inequality sign. You get it on the cheap in some sense, right? Okay, and then what? So let me write for you that this is actually in quadrant 1 as well, right? So alpha over 2 is still in between 0 and pi over 4, which means still in quadrant 1. And then what can you say about sine of alpha? Well, if alpha is in quadrant 1, the sign there is positive, right? The sign there is positive in quadrant 1. Sine and cosine actually are positive, so sine is positive. How about the tangent of alpha over 2? So alpha over 2 is still in quadrant 1. So the tangent is going to be sine over cosine, right? So tangent of alpha over 2 is the sine of this angle alpha over 2, right? Divided by the cosine of that angle alpha over 2. So in this context, alpha over 2 is in quadrant 1, so the sine of that angle is positive, right? Because alpha over 2 is in quadrant 1. I'm talking about the first column. Alpha over 2 is still in quadrant 1, so that guy is positive. How about cosine of that guy? Isn't that also positive in quadrant 1? So positive divided by positive is positive, right? So this is positive. Makes sense? Let's move on to the next column. If alpha is between, or if alpha is in quadrant 2, again, I'm going to still talk about the first revolution. So if alpha is in quadrant 2, what does it mean to be in quadrant 2? It means that, and while talking about the first revolution, it means that alpha is between pi over 2 and pi, right? Okay. What can you say about alpha over 2 then? How about also dividing through by 2? And again, since you divide by a positive entity, you do not have to pay any price, right? The inequality signs remain the same. Pi over 2 over 2 is pi over 4. And you divide this by 2, you get pi over 4, right? Pi over 2. I'm dividing through by 2, so this becomes pi over 2 here, right? Okay, so in which quadrant then alpha over 2? So alpha over 2 is between pi over 4, which is 45 degree, and pi over 2, which is 90 degree. So alpha over 2 remains in the first quadrant. So this is still in the first quadrant, right? Okay. Now, what's this guy? What's this sign here? The sign of sine alpha. Alpha is in quadrant 2. What's the sign there? Is it positive or negative? Quadrant 2, the sign is positive. It's the y value, right? Okay. And how about tangent of alpha over 2 this time? Well, tangent of alpha over 2 is still sine of alpha over 2 divided by cosine of alpha over 2. And we just said in this context, in the second column context, alpha over 2 still in quadrant 1. So the sine of alpha over 2 remains positive and the cosine of alpha over 2 remains positive because this angle alpha over 2 in this discussion is still in quadrant 1, right? Still in quadrant 1. So what's the sign here then? It's positive, right? Okay. Third column. Let's move on to the third column. Okay, so the third column is about alpha being where? Alpha now is in quadrant 3. And quadrant 3, while talking about the first revolution, means that alpha is between pi and 3 pi over 2, right? And as such, what can be said about alpha over 2? If you divide through by 2, you get here alpha over 2, the middle piece, and then the lower bound becomes pi over 2, and dividing this by 2 means 3 pi over 4, correct? Okay. So what can be said about alpha over 2 then? Alpha over 2 is in which quadrant? What's this angle? This is 90 degree, and this is 3 pi over 4, so this is 90 degree plus another 45 degree, so that's 135 degree. So this is in the second quadrant. So this is in the second quadrant. Alpha over 2 as such is in the second quadrant. If alpha is in the third quadrant, alpha over 2 is going to be in the second quadrant based on the analysis we just talked about here. Okay, so how about sine? Sine of alpha. Well, alpha is in quadrant 3. What's the sine of the angle in quadrant 3? The sine, okay, let me give you a small picture. So if this is an angle here in quadrant 3, so that's the angle. And so this is such an angle alpha in quadrant 3. The sine of such an angle, so the sine of such an angle, so the terminal point is here, the sine is going to be negative, right? So that's going to be negative then. That's going to be negative. Okay. How about tangent of alpha over 2? Well, alpha over 2, it's in quadrant 2. Alpha over 2 is in the second quadrant. So alpha over 2 is in the second quadrant, maybe something like this. Okay. So this is that angle can be alpha over 2 in the second quadrant. And what do you know about the sine, the second coordinate? The second coordinate is positive, so that guy is positive. And the first coordinate, which is cosine, is negative, right? So how about the tangent of such an angle, alpha over 2? It becomes positive divided by negative. And what's positive divided by negative? It's negative. So we complete the third column. And lastly, the fourth column, I'll leave it as an exercise for you. I'll complete it, but please understand what's going on here. So this is going to be quadrant 2, that's going to be still negative, and that's going to be negative. And here, if you go back to the book, the question here is, what do you notice about the signs of sine alpha and tangent of alpha over 2? And what we notice about the sine of this function, sine alpha, and the sine of this function, tangent alpha over 2, is that they are the same, right? So let me erase this part. We notice that they are the same. They have the same sign, not they are the same. So we notice that sine of alpha and tangent of alpha over 2 have the same signs for all alpha, right? For all alpha. Obviously, as long as tangent of alpha over 2 makes sense. Okay. What I mean here is alpha should not be an angle that makes tangent of alpha over 2 undefined, right? For example, if alpha is pi if alpha is pi, tangent of pi over 2 doesn't make sense. That's my point. Okay, but as long as both of these entities, tangent of alpha over 2 and sine of alpha, as long as both of them are meaningful entities, then what we just discovered is they must have the same sign. They must have the same sign. Okay. All right, so we're gonna take this knowledge and try to use it very soon. Last group of formulas, half angle formulas, that's gonna connect, as we said before, that's gonna connect half the angle. Look at this. If the angle is u, this is half of u, and it's gonna connect it to u itself, right? I mean, somehow. I'll explain where these formulas come from just shortly. Okay, so sine acting on half of u, I have a relationship between this and cosine of u, so the full angle. Similarly here, half the angle connected to the full angle, and likewise here, half the angle is connected to the full angle, right? Okay, so where do these formulas come from? Well, they come from the power reducing formulas just above. Look at this. If you go back to that, let me take you back to this, to the power reducing formulas. So just a second, let me just go back to these formulas. Where are they? Right here. You see this? Sine squared x equals 1 minus cosine 2x divided by 2. If you replace x by u over 2, you get sine squared of u over 2 equals 1 minus cosine of 2 times u over 2. And what's 2 times u over 2? Simply u over 2. So we get sine squared of u over 2 equals 1 minus cosine of u over 2, right? So let me take you back to the page where we are. So, so the power reducing formulas let me just remind you of what we just talked about. So sine squared x equals 1 minus cosine 2x over 2, right? So we have this, and if you replace x by u over 2, as we just said, that's gonna be u over 2 here, right? And as such, this formula becomes, just take this out, replace it by u over 2, and take this out, replace it by u over 2. And if you replace it by u over 2, 2 times u over 2 is simply u, right? So all this can be erased, and you only get here the u. So you get this formula. And then what does this mean? Doesn't it mean that sine of u over 2 is equal to plus or minus the square root of 1 minus cosine of u over 2? Correct? And plus or minus is determined by where u over 2 lives. Depending in which quadrant it lives, you determine the sign, right? So this is the formula here. And cosine of u over 2 to equal plus or minus square root of 1 plus cosine mu divided by 2, that's also going to come from the power reducing formula for cosine. Okay, so again, by replacing the x in the power reducing formula by u over 2, we get, so it's the same discussion, we get that. Again, the plus and minus are determined by where u over 2 lives. And finally, these two formulas for tangent of u over 2, let's try to, hold on just a second. So let me just erase this part and try to prove the last one for you. So let's prove the last one. So we know from the power reducing formula for tangent that what? The following holds. Tangent squared x is equal to 1 minus cosine of twice x divided by 1 plus cosine of 2x, right? Over here, I'm going to replace, as we've been doing, I'm going to replace x by u over 2. So each time I see x, I'm going to replace it by u over 2. Okay? So this formula becomes tangent it's the same, tangent squared of u over 2 equals 1 minus cosine of twice half of u, which means u, divided by 1 plus cosine of twice half of u, which also means u, right? So we get this. Okay. Again, my eye is here. My eye is on this. Let's prove the first equality and explain why the second holds. How about now we multiply and divide by 1, but this one is going to look like 1 minus cosine of u divided by 1 minus cosine of u. This is a 1, right? I mean, it's the same thing, upstairs and downstairs. So if you divide again, you get 1. So technically I didn't change anything, but I wrote 1 as such. Why, you're gonna see shortly. What is that? What is that? So upstairs I have 1 minus cosine of u times itself. So I have the square of 1 minus cosine of u. And downstairs I have 1 plus cosine of u times 1 minus cosine of u. That's downstairs, yes? Okay. And let's recall this formula, a minus b times a plus b. If you forgot it, FOIL it out. You should get a squared minus b squared. Okay. So here we get then, you see downstairs, it's of the form a minus b times a plus b. Okay, maybe a plus b times a minus b, same thing. Okay, you know what, just to still talk about the same form, the same structure, this is still the same thing, right? This is still a plus b times a minus b. I mean, this is the same as I had before. A minus b times a plus b, or a plus b times a minus b are the same. Okay, because multiplication is commutative. So long story short, downstairs now look like a plus b divided by or times a minus b. Okay, so as such, this property tells me I'm gonna get a squared, so 1 squared, and what's 1 squared is 1, minus the square of cosine of u. We get this, right? And upstairs I get 1 minus cosine of u squared. Okay. And then how about appealing to the Pythagorean identity? The Pythagorean identity says sine squared of the angle, let's call it u, equals 1 minus cosine squared of u. Remember this property? Okay, so which means downstairs, this guy, 1 minus cosine of u, is sine squared of u. So downstairs, that's the same by the Pythagorean identity, sine squared of u. And upstairs, I have the square of 1 minus cosine of u. Okay, so we are at this point. Tangent squared of u over 2 is equal to this quotient. Let me summarize it. So we have tangent squared of u over 2 is equal to this quotient. So this quotient here, 1 minus cosine of u squared sine of u squared, right? Sine squared of u is sine of u squared. So you know what I'm gonna do? I'm gonna try to write the whole thing like this. The whole thing squared. Makes sense? Because the square upstairs, the square downstairs, I can just put it in factor in some sense. So it's the square of the whole quotient. Okay? And so I have square here, square here. This means that tangent of u over 2 is equal to plus or minus the square root of the square of 1 minus cosine of u divided by sine of u, right? So we get this. And what's the square root of the square of something? You don't know what this thing is, maybe positive, maybe negative. So it's going to be the absolute value of this thing, right? It's going to be the absolute value of the thing. So what I'm saying here is recall that square root of a squared, if a is a real number, is the same as the absolute value of a, right? It depends what a is. It depends what a is. If a is positive or non-negative, the absolute value of a is going to be a, and if a is negative, the absolute value of a is going to be negative a. Alright, so this is then equal to plus or minus the absolute value of 1 minus cosine of u divided by the absolute value of sine of u, right? And maybe in 2 steps would be better, something like this, right? But the absolute value of a quotient is the quotient of the absolute value, so we get this. Okay. Sounds good. Okay, so next, cosine of u. What do you know about cosine of u? What's the largest number cosine of u can reach? Isn't 1? So isn't cosine of u always less than or equal to 1? For all u, no matter what u is. So for all u, doesn't that mean also that 1 minus cosine of u is bigger than or equal to 0? Right? If you subtract both sides by cosine of u, don't you get 0 less than or equal to 1 minus cosine of u, which means 1 minus cosine of u is at least 0. Okay, so this entity here, see this guy? So this entity here is bigger than or equal to 0. So what can you say then about its absolute value? The absolute value of something that's at least 0, something that's non-negative, is itself. Right? So this guy is going to be needed now here. And this is plus or minus 1 minus cosine of u divided by the absolute value of sine of u. Again, I drop the bars because the guy inside the bars is non-negative. And if the guy is non-negative, the absolute value of the guy is itself, right? So the absolute value become decoration only. They're not doing any job. All right, and then we're here. So far, this is where we are. We have that tangent of u over 2 is equal to plus or minus 1 minus cosine of u divided by sine of u. Yes? With the absolute value. All right. And what did we just do in problem 45? What did we just do in problem 45? Over here. What did we just do? We just noticed that sine of alpha and tangent of alpha over 2 have always the same sign, no matter what alpha is. This guy, sine of alpha and tangent of alpha over 2 are of the same sign. So back here, so by the problem just done above, tangent of alpha over 2, in this case alpha is u, so tangent of u over 2 and sine of u have the same sign, correct? So they have the same sign. For example, let me just talk about it, and then let me just talk about it here on this space. If sine of u is positive, okay, cannot be 0 because it's downstairs. If this guy is positive, what is the absolute value of the guy? What is this? Isn't it itself? Because the absolute value is not doing anything anymore, because that sine guy is, I mean, the sine of u is positive. So you get this, right? Okay. So as such, tangent of u over 2 becomes plus or minus, which is to be determined, 1 minus cosine of u divided by sine of u, right? And the question is, which sign is it, the plus or the minus? Which one? Well, in this case, this is a case where sine of u is positive, right? I'm talking about this case. Let's call it case 1. So since sine of u is positive, the bars drop, so downstairs becomes this. And then the question becomes, which sign should I choose, plus or minus? Well, we just talked about it. So tangent of alpha over 2 is of the same sign as the sine of u, right? Of the same sign. So in this case, this guy is positive. In our case, this guy is positive, right? And how about the guy upstairs? This guy upstairs is bigger than or equal to 0 all the time. Remember this green thing here? This guy upstairs is always non-negative, correct? So the worst it gets is 0, but most of the time is positive. And tangent of u over 2 have the same sign as sine of u based on problem 45. Since the sine of u is positive, that guy should also be positive. So since upstairs is non-negative, that's gonna force this to be plus, correct? That's gonna force this guy to be plus. So so what do we get? We get in this case then, so in this case we get tangent of u over 2 is equal to plus 1 minus cosine of u over sine of u. Agree with that? So in this case, case 1, if we assume that sine of u is positive, we get the tangent of u over 2 to be plus that guy. Now the other case, case 2, if sine of u is negative, then what can you say about the absolute value of sine of u? Isn't it minus sine of u? So the absolute value of a negative number, isn't it the opposite of the number? So this whole thing becomes positive. Okay. So tangent of u over 2 is going to be plus or minus, to be determined, 1 minus cosine of u divided by this absolute value, which is in this case minus sine of u. So tangent of u over 2 in this case is going to be plus or minus, again, to be determined, 1 minus cosine of u over negative sine of u, right? Because we drop the bars. So if you drop the bars in this case, because in our case now sine of u is negative, we're gonna pick up a minus sign, right? All right. So this guy upstairs is at least 0. Downstairs, what can be said about this guy downstairs? So sine of u is negative. How about minus sine of u? If sine of u negative, its opposite is going to be positive, correct? Its opposite is going to be positive. So what can be said about this whole quotient? This whole quotient, how about this for a color? This whole quotient is greater than or equal to 0, right? Okay, So it's most of the time positive. It's most of the time positive. By the way, I mean, this cannot be zero in this case. I mean, the only time this is zero is when 1 minus cosine of u is zero, and this happens when cosine of u is 1, right? When cosine of u is 1. But when cosine of u is 1, sine of u is 0. And sine of u cannot be 0 because it's a denominator. So I can safely say, okay, I can erase this equality, correct? One more time. I know that 1 minus cosine of u is at least 0, so it's 0 or more. But look, if it's 0 upstairs, if 1 minus cosine is 0, means cosine of u is 1. And if cosine of u is 1, this forces sine of u to be 0, which means I'm dividing by 0, and this cannot be the case, correct? So upstairs should be positive for this quotient to exist. Agree with me? Otherwise, I would be dividing by 0 if upstairs is 0, because it forces sine of u to also be 0. Okay, so upstairs is positive. Similarly here, I can also erase this minus, this equality sign for the same reason. So upstairs positive, downstairs positive, this whole block is positive. And what's the sign of tangent of u over 2 in this case? Since tangent of u over 2 is based on problem 45, since the sign of this guy should be the same sign as the sign of u, which is negative, that guy should be negative, right? That guy should be negative, correct? So which sign should we choose? The plus or the minus? Since this guy should be negative, so we should choose the negative sign, because the negative times this quotient, which has positive sign, is going to turn the whole thing into negative, right? So that sign is going to survive. That sign is going to survive in this case. And how can we write the whole thing then? So we can write it in this case to be tangent of u over 2 equals minus 1 minus cosine of u divided by minus sine of u. Agree with that? Because we choose the minus sign to turn the whole thing into negative, because that guy is negative. So we get this, right? We get this. And this minus with this minus, if they talk to one another, what do they get? What do we get? We get plus. So we get tangent of u over 2 equals 1 minus cosine of u divided by sine of u. Correct? If this minus talks to this minus, minus times minus is plus. So we get this. So we get this. Let me box it for you. And let me box the previous one for you. This one here. Okay, and what do we infer? These are the only two cases for sine of u, this guy, sine of u. Sine of u cannot be 0, so it's either positive or it's negative. It's either case 1 or it's case 2. And in both cases, this whole expression turned out to be this block or this block. But these, I mean, look at this, look at those blocks. Aren't they the same? Aren't they the same? So it doesn't matter whether we are in case 1 or in case 2, which are all the cases for sine of u, because sine of u is either positive or negative, it cannot be 0. In both cases, tangent of u over 2 turned out to be 1 minus cosine of u over sine of u. Make sense? So based on this small discussion here, tangent of u over 2, I can write this whole thing as 1 minus cosine of u divided by sine of u. And the reason is behind the discussion just below. All this discussion is what helped me conclude this formula, right? Again, I transitioned from this equation to this equation because I considered all the possible cases, and in all the possible cases, it turned out that this expression and this expression are actually the same. They are equivalent, the same thing. Okay. All right. So this is this formula right here. So this is the proof of this formula, the first equality. Okay? So this is the proof of this equality. Now, you're going to tell me, how about the second equality? Well, I'm not going to do the second equality. I'm going to tell you what to do, though. To prove the second equality, remember here we multiplied by 1 minus cosine of u divided by 1 minus cosine of u. If you multiply by 1 plus cosine of u divided by 1 plus cosine of u, you're going to get exactly, and you continue the same way, you're going to get exactly this one. You see the plus? You're going to get exactly this one. Okay? But the treatment is the same. All right, so let's keep going. So we have these formulas then at our disposal. We can use them whenever we want. All right, back to the book. How about doing now number 44? The question is, use half angle formula to find the exact value of sine pi over 8. So that's number 44. So we want to find the exact value of sine of pi over 8. So, and they told us should just use half angle formula, but if they didn't tell us this, I hope you see that this is half of a remarkable angle. Pi over 8 is not remarkable, right? It's half of a remarkable angle, and that angle is pi over 4. Half of pi over 4 is pi over 8, correct? So that's half of pi over 4, correct? And now I'm gonna use the half angle formula for sine, which is what? If you go back to the formulas above, this is sine of u over 2 equals plus or minus, to be defined, square root of 1 minus cosine of u divided by 2, right? And the idea is to determine the sign. Is it plus or minus? We're going to see shortly. So I'm going to apply this. Plus or minus the square root of 1 minus cosine of the angle. And what's the angle here? Who's playing the role of u? It's this guy who's playing the role of u, right? So this is sine of half of u, right? Half of u means u over 2, right? So half of u is equal to plus or minus square root of 1 minus cosine of u, and u is, as we said, pi over 4. The whole thing is divided by 2, right? So we have this. What's cosine of pi over 4? Oh, before I do so, how about we choose the sign? How about we determine the sign? Is it plus or minus? Which one is it? Well, pi over 8 is in the first quadrant, right? It's half of 45 degrees. It's half of 45 degrees, so certainly it's positive and in the first quadrant. So sine in the first quadrant, is it positive or negative? Which one is it? In the first quadrant, sine is positive, right? It's the y-coordinate of a terminal point. So it's going to be positive, so it's not the minus. How about we erase it? And then I get this. Okay, so now we know the sign, and then how about we find each piece? Cosine of pi over 4 is square root of 2 over 2. So that's going to be plus the square root of 1 minus square root of 2 over 2 divided by 2. Why? Because cosine of pi over 4 is square root of 2 over 2. Okay? All right, this is a good answer, but again, if you want to simplify it, how about making the same denominator upstairs? How about making the same denominator upstairs, which is 2, so we get 2 minus square root of 2, right? How did I get that? I made the 1 as 2 over 2, and I glue them together. I get this. And this is of the form a over b, and the whole thing is over c. We discussed this above. This is simply a over b times c, and 2 times 2 is 4. So we get 2 minus square root of 2 minus square root of 2 divided by 4. Okay, so we get this. And then, all right, if you want to simplify this, This is the same as square root. Square root of a quotient is the quotient of the square roots, right? So square root of the guy upstairs divided by the square root of the guy downstairs. And downstairs is 2, right? So we get this. Okay. All right. Next, let's go back to the book. All right, so how about doing a problem here? So one of these problems, verify the identity. And let's go to the last one, 56. So we want to show that cosine squared of x over 2 minus 3 times sine squared of x over 2 plus 1 is equal to 2 cosine of x. Okay. So this is number 56. So number 56, we want to show the identity or verify the identity. Cosine squared of x over 2 minus 3 sine squared of x over 2 plus 1. We want to show that this is simply 2 cosine x. Okay. All right. What do we know about? I mean, there are many ways to do it. How about the following? Let's recall that cosine squared of theta minus sine squared of theta. I hope you find a different way to transition from the left hand side to the right hand side. And this is the first that came to my mind. This is the same as a cosine of 2 theta, right? It's the double angle formula, the very first formula or group of formulas we learned today, and we showed this, right? Cosine of twice the angle is cosine squared of the angle minus sine squared of that angle, right? So why this is going to be useful? So the left hand side is equal to cosine squared of x over 2 minus sine squared of x over 2 minus 2 sine squared of x over 2 plus 1. Why is that? What did I do? I split the minus 3 as minus 1 and minus 2. And if you go back, you see it. Minus 1 sine squared of x over 2 minus 2 sine squared of x over 2. This is still minus 3 sine squared of x over 2. Okay? Why did I do so? Because, as we said, I just recalled this thing. And look now. Don't you have a format like this? So certainly theta is x over 2 in this case. So this is of the form cosine squared of theta minus sine squared of theta. And this is what? Cosine of 2 theta. This is cosine of 2 theta. So cosine of 2 theta, and theta is x over 2, right? What did we use? We simply used this asterisk. So we use this asterisk over here. Okay. Minus 2 sine squared of x over 2 plus 1, right? Agree with that? How about we recall this again? Let me take all this down a little bit. And let's recall another formula. We also know that cosine of 2 theta, we know that this is equal to how much? Another way to represent cosine 2 theta, I know one. I have 3 ways, right? Remember? And another one is 1 minus 2 sine squared of theta, right? Again, go back to the double angle formula and you're gonna see it. How about we label this as double asterisks? And where am I gonna use it? I'm gonna use it right here. Let me set the stage for it. So this is cosine of 2 divided by 2 is 1, so this is simply cosine of x, right? 2 divided by 2 is 1, minus, I'm gonna push a minus in factor, so I'm gonna get inside 2 sine You know what? I don't need to push a minus to set. Okay, one more time. Let me try again. So this is the same as plus 1 minus 2 sine squared of x over 2. Okay. I just wrote them. I reversed the order. So, right? Addition is commutative. So something plus another is the same thing as the latter plus the former, right? You get this? All right. And now do you see that this is actually cosine of twice x over 2 because of double asterisk. Again, look, 1, 1 minus 2 times sine squared of this angle. So whose theta is x over 2. If you see theta as x over 2, certainly this bracket has the right-hand side structure of double asterisk. And this tells you that this is cosine of 2 theta. Okay? And theta is x over 2. So this is then equal to cosine of x. And here I used double asterisk. Okay, so we get cosine of x plus what? Cosine of twice the theta, which is x over 2. All right, and this is x, right? So this is again cosine of x plus cosine of x, which is 2 cosine of x. And this is the right-hand side, the desired right-hand side. Okay, this is the desired right-hand side, 2 cosine of x. All right, back to the book. All right, let me see which problems to choose from. How about a problem here like 82? Find an algebraic expression representing sine of 2 cosine inverse of x for x between 0 and 1. Okay, so 82. Zoom in. We want to find an algebraic expression representing the entity sine of 2 cosine inverse of x. And this is going to be for x between 0 and 1, possibly 1. So we're going to find an algebraic expression. Remember, algebraic expression in x means no more trig functions, no more transcendental functions, okay? No more trig or their inverses. All right, so we've done these before, but this is the first time we have twice inverse function acting on something. All right, how about we call this guy theta? So theta is cosine inverse of x. So theta is going to be in the range of cosine inverse. So theta is going to be where? What's the range of cosine inverse? Is 0 pi, right? If you recall that. So theta is in 0 pi, so it's either in the first or second quadrant. I'm trying to see what information I have. Okay, that's it. So theta is either in the first or in the second quadrant. Okay, and this now becomes sine of 2 theta, right? Sine of 2 theta, and this is a sine acting on twice the angle, and if you appeal to the double angle formula for sine, you would get 2 times sine of theta times cosine of theta. Agree with that? 2 times sine of theta times cosine of theta. Okay. Do we know any of the two ingredients? And by two I mean this or that. Yes, we know this one, right? We know cosine of theta. Why? Because look at this. This is equivalent because cosine inverse, this is the inverse function. By definition of inverse function, this is the same as cosine theta equals x. Correct? Out of this, you can say that cosine theta is x. So how much is this then? This is x. It's right there. Okay, so this guy is x. Now the question is, how much is sine theta? How much is sine theta? Let's take it in green. So who's that? How about we find it? How about we find it here? Well, you know cosine of theta and you know where theta lives. So don't, how do you find sine theta? Back to Pythagorean identity, right? Sine squared of theta is equal to 1 minus cosine squared of theta. Oops, cosine squared of theta. And what's cosine of theta in our discussion? Cosine theta is x, so what's the square of cosine theta? Is the square of x. Okay, so this means sine of theta is plus or minus the square root of 1 minus x squared, right? The square root of 1 minus x squared. And the question is, it plus or minus? Well, it depends where theta lives. It lives in between 0 and pi. So it's either in the first quadrant or in the second quadrant. What do you know about sine here? Sine is the y value, so it's certainly positive. Sine is certainly positive. So we get the positive sign, right? We get the positive sign. We get the positive sign since theta is in quadrant 1 or 2, right? Okay, very good. So that guy then, this package here, is gonna allow us to write. So this is known at this point. We don't have it unknown anymore. So we get 2 times sine theta, which is plus the square root, so square root of 1 minus x squared, times that guy, which is x. Okay, so we get 2x square root of 1 minus x squared. Typically people write the square root at the end. It's customary to do it this way, but there's nothing wrong with this writing. But this is again it's more traditional. Alright, so this is the algebraic expression that represents this writing, this expression. This is a trig expression. And this answers the question, right? Okay. Let's do one more problem. Let's go to the very last problems here. How about we do the last one, number 100. Okay, so verify the identities for a right triangle ABC. So we have this picture ABC, and we want to show that tangent of A over 2 is equal to C minus B over A. Okay. All right, so we have the picture, and we want to show, as we said, we want to show that tangent of A over 2 is equal to C minus little c minus little b divided by little a, right? All right, so this is what we want to show. Keep in mind that A is the angle, this is the angle A, right? And C is the 90 degree and B is this angle. Okay, so we just a number 100, we care about A, so we don't care about the angle B now. All right, so how can we get our hands on tangent of A over 2? Well, first of all, we don't have A over 2, we have angle A, right? This is angle A. I want to transition to angle A, given that I have to deal with tangent of A over 2. What's the relationship between tangent of A over 2 and something that relates a trig function to A? Well, this is one of the half angle formulas we just learned at the end. This is, let's say, 1 minus cosine of u, but u in this case is A, divided by sine of A, right? Correct? This is the formula we just showed above. We have a different one, so they are the same. Just pick one. At home, how about you pick the other as well? Just do it in two different, just using the two different formulas, yet they are the same, so they're gonna get the same answer for sure. Okay. So I related tangent, the trig function tangent acting at half the angle A to other trig functions, cosine and sine in this case, acting at the full angle A. Alright, so now I can use the picture to actually find this quotient. Correct? Alright, and what's cosine of A? How about we write it here next to the picture? Cosine of A. Cosine of A. Well, using the right triangle, cosine of an angle is the adjacent side, the size of the adjacent side, which is B in this case, over the hypotenuse, and the hypotenuse is C, of length C, right? So cosine of A is B over C. And how about the other entity, sine of A? Sine of A, well, sine of an angle is the opposite side, the length of the opposite side, which is A, little a, divided by the hypotenuse, which is of length C. Okay? So as such, what do we get here? This is then equal to the quotient 1 minus cosine of A. And what's cosine of A? B over C, divided by sine of A, which we just found to be little a over little c. Okay? All right. This is okay as an answer, but the problem is they told us to show that this is equal to this, so we need to do some aesthetics. Okay. How about the same denominator upstairs as being c, which means that you want to see the 1 as c over c, so this becomes c minus b upstairs, divided by a over c. Okay. And what is this? What is this? So let me convince you that this is the desired conclusion by just talking here about something of the form x over y divided by z over y. Now what is this algebraically? This is x over y divided by z over y, right? And dividing by z over y is the same as multiplying by the reciprocal of z over y, right? So which is, what's the reciprocal of z over y? Isn't it y over z? Alright, and this is xy over yz, x times y, over y times z. And the cancellation occurs at this point, right? So you can cancel the y and the y. And this is equal to simply x over z, right? So all this is gonna help me to simplify the writing. How about we label capital S, X, capital Y, capital Z? This is the capital X in the discussion in the bubble here. This is the capital Y in the discussion. So it's the same Y, right? And then the Z is the A. The Z is the A. And what does this algebra tell me here? Tells me, well, this is X over Z. All this quotient is simply X over Z. So it's C minus B over Z, which is A. Correct? As desired, no? This is not what we wanted. This is not what we wanted. This is C minus B over A. C minus B over A. Okay, so that's the end of the section.